Hey, good morning, everyone. Thank you for joining my presentation. I'm Mahshid Ghanbari, a PhD student at Colorado State University, and today I want to talk about my research on increasing risk of compound flooding under climate change. So flooding has caused significant losses to people and property across the world during the course of last decades, and climate change is putting a greater pressure on cities by increasing the frequency and intensity of flood events. Extreme coastal events such as a storm surge by Hurricane Harvey is happening more during recent years, and minor coastal events, or in other words, tidal or nuisance flooding, are happening with more frequency and have become a serious challenge in coastal cities. More extreme precipitation have also increased fluvial or urban flooding and also fluvial or riverine flooding. The pressure on coastal cities are higher because they are exposed to different types of flooding, such as tidal flooding, storm surge, and riverine flooding. If these events occur simultaneously or in close distance, the impact of flooding may increase. And if we ignore this coastal river flood interaction, we may underestimate the flood risk. An example of recent compound flooding is the co-occurrence of heavy precipitation and storm surge from Hurricane Harvey, which caused huge flooding along the Gulf coast of Texas. So in regions where total flood depth is influenced by both extreme river discharge and extreme seawater level, considering the simultaneous occurrence of these two events is important to estimate future flood risk. The previous studies shows that the number of these compound events has increased over the past century at many coastal cities, and this can be associated with the climate change. So it is important to examine the compound risk from coastal and riverine flooding with considering the impact of climate change. Sea level rise may be deemed as the most important impact of climate change in coastal regions. Here you can see the National Climate Assessment Sea Level Rise projection. And what we can see here is that the global mean sea level has been increasing over the past decades. And the rate of it is anticipated to accelerate over the 21st century. And also we can see that there is a great uncertainty in the future projection of sea level rise. Climate change is also influencing extreme hydrological events such as changes in extreme heavy precipitation intensity and frequency, which subsequently may lead to increase in extreme stream flow discharge. And these changes have an immediate impact on increased riverine flooding risk. So with this information in mind, the main purpose of our study is to develop a bivariate non-stationary flood hazard assessment model that accounts for compounding effect of coastal and riverine flood events with consideration of climate change, including sea level rise and also variation in stream flow discharge. And then to use this methodology to estimate the future joint return period of compound major coastal riverine flooding, and also estimate the future annual risk of coastal and riverine flooding in terms of failure probability. Since we are interested in estimation of flooding hazard, we need to apply the bivariate model just to pairs of high values to prevent representation of extreme values with bias. So we use a peak over threshold method to identify extreme seawater level and river discharge data. And the basic idea behind this approach is to choose a threshold and to study the statistical properties of all exceedances over threshold for a given period of time. And it can be assumed that the exceedances above threshold follow a generalized Pareto distribution, or simply GPD. Then we select the pairs when seawater level and river discharge value exceed the threshold simultaneously to finally have the pairs of extreme seawater level and river discharge. And then these pairs of data should be fitted to the bivariate model. Several parametric and non-parametric methods can be used for bivariate analysis. We decided to use Copula method since using this method, the marginal distributions can be selected without any limitation. So for random variable x and y, there is a unique copula that describes the dependence structure between the random variables with marginal distribution of fx and fy. So we need to know the marginal distributions of the random variables and also their joint distribution using copula. In general, the procedure is first to fit the best univariate distribution to the marginals. And then since we use peak over threshold method to identify extreme pairs, non-stationary GPD is used as a marginal distribution. And then the best copula is selected among 25 different copulas based on the Bayesian information criteria. As I mentioned, our main goal is to incorporate the effect of climate change in our bivariate flood hazard assessment. So either the marginal distributions or the dependence structure between variables or both can be non-stationary. In this study, we consider the non-stationary effects of climate change in marginal distribution of seawater level and river discharge. And in order to do this, we use projected sea level rise scenarios and also projected streamflow discharge under different climate models. So one more point before I get to some results. Unlike univariate analysis, joint return period is not unique in bivariate analysis, and several definitions of joint return period are available in the literature. Suppose that X star and Y star are hypothetical coastal and river flood thresholds. Then we can have two different joint return periods based on two hazard scenarios. Or hazard scenario which consider exceedances above either coastal or river flood threshold or both. The OR scenario should be considered for computing risk since either exceeding over coastal or river flood threshold or both is sufficient to produce flooding events. And hazard scenario, consider the situation when both scenarios happen simultaneously. I mean that both river and coastal flood threshold are exceeded. This scenario should be considered for hydraulic modeling, which we need to know the probability of simultaneous occurrence of high seawater level and river discharge. We use the data from tidal and river station at the Potomac River estuary in Washington, D.C. as a case study to demonstrate the application of our method. The green circle shows the location of Washington, D.C. tidal station, which is operated by NOAA. And the red one is Little Falls River Station at Potomac River, which is operated by USGS. For coastal component, we need three sets of data. Hourly observed sea level data from Washington, D.C. tidal station, also the major coastal flood threshold, since we are interested in characterization of major coastal river flooding. This data was obtained from the report by Sweet, and also regional sea level rise projection scenarios, which was obtained by another report by Sweet. For riverine component, we need four sets of data. First, daily river discharge from Little Falls River Station, also major riverine flooding threshold, and also the stage discharge relationship for converting discharge values to depth, which all of these data were obtained from USGS website, and finally simulated a streamflow discharge for incorporating non-stationarity in our model, which for this study, we use simulated streamflow discharge driven by the variable infiltration capacity, or simply WIC model, with 10-member projections of precipitation and temperature under RCP 8.5. We used these data to explore the dependence between extreme seawater level and river depth in Washington, D.C. So after feeding the marginals to the GPD and selecting the best copula, we created the joint non-exceedant probability isoline, which you can see them in the left figure by gray lines, compared with the empirical joint non-exceedance probability isoline, which here are shown by the red line. In the right figure, you can see the current joint return period of simultaneous exceedance of different sea water level and river depth based on the AND scenarios. And so you can see that the current joint return period of major coastal river and flooding is 105 years. However, as I discussed earlier, these values is not constant under climate change. So in the first step, we estimate the joint return period of major coastal river and flooding under different sea level rise values. You can see the result in the left figure. For example, we can see that 10% decrease in joint return period of major coastal river and flooding could happen under 0.7 feet sea level rise. Then we used projected sea level rise scenarios to determine the time when indicated sea level rise are anticipated to occur. So we can see this 10% decrease in joint return period of major coastal river and flooding might happen by the year 2035 and 2045 under intermediate high and intermediate sea level rise scenarios, respectively. In the next step, we also consider the effect of variation in streamflow discharge and estimation of future joint return period of major coastal river and flooding. In the right figure, you can see changes in the joint return period under just intermediate sea level rise scenario, which is shown in the right blue, and intermediate sea level rise scenario with ensemble of stream flow prediction in dark blue, and then the combination of intermediate sea level rise scenario and driest and wettest stream flow projections are also shown by green and red dashed line, respectively. The point here is that the effect of sea level rise on changes in joint return period of major coastal river and flooding is higher than impact of increasing stream flow discharge. For example, by the mid-century, we can see that there is almost 20% decrease in joint return period of major coastal river and flooding, which almost 15% of that is due to sea level rise. Then we use the ore hazard scenario to estimate risks in terms of failure probability. Traditional stationary failure probability is 1 minus bivariate non-exceedance probability to the power of temporal horizon, which cannot be used in the case of non-stationary condition. So we use this equation, which first derived by Dr. Salas in 2014 for univariate analysis. And then using 6 sea level rise scenarios, we estimate the increase in failure probabilities due to compound major coastal river and flooding. And also failure probability under stationary condition is also presented by dashed black line for the sake of comparison. These results show the importance of considering sea level rise in estimation of failure probability and how ignoring the effect of sea level rise leads to underestimation of future risk. So in conclusion, this study developed a bivariate non-stationary flood hazard assessment that account for compounding effect of coastal and river and flooding events with consideration of impact of climate change, including sea level rise and variation in stream flow. And then we found that ignoring the effect of climate change on individual flood components may lead to inappropriately underestimate the compound flood probability. And also we found that sea level rise is more important to consider in estimation of future compound flood risk compared to the variation in stream flow discharge. Thank you.
Thanks, Mahshid. Well, I'll open it up for questions now, so you can enter those into the chat queue or raise your hand and I'll turn your microphone on. Okay, Tim, it looks like you should be cleared.
Yes, hi, this is Tim Green. Thank you for the presentation. Couple of questions. One is, so when you look at sea level rise, you have a combination of larger scales and smaller scales and say storm surge, and then the probability of storm surge combined with river stage rise. So I was just wondering how you separate, say, those different components of sea level rise, and then with Chesapeake Bay, you have a very unique geometry. How would that compare with other parts of the world?
So this is a good question. We consider the all combination of seawater level, I mean the tide, the mean sea level, and also the storm surge together. And we didn't separate that because this is just a simple statistical analysis, and we are not want to model this stuff. So we just use the combination of the seawater level. So our seawater level is the combination of the mean sea level, the tide, and also storm surge. We didn't separate that, yeah.
So do you have any sense of how it would compare to, say, a more open coastal area?
I don't know. Our plan is to use this statistical method for all the US, and I don't know what would be the result for the other coast, or I don't know.
Okay, thank you.
Sure.
Okay, well, I haven't seen anything else come up and there's no other hands raised. So if there aren't any more questions at this time, I'll go ahead and get us transitioned to our next presenter. Thanks for your time, Mahshid. Have a good day.
Thank you, you too.